Okay. In this video, I'm going to try to introduce this idea of mechanisms. And to do this, I'm going to go back to a general chemistry textbook so that we can avoid some of the language that appears in your textbook. And why I'm doing this is I'm really trying to set up the stage for the next videos, the videos for section 14.2. Because in 14.2, we're going to actually put the full the full definition of mechanisms with the approximations that we are making that we're really showing in this video, but we're not going to work through the math in such of a detail. But I want to make sure that you are remembering these ideas of finding the overall rate law from a mechanism, putting together elementary steps. We did this in Gen Chem, but I know it's been a while, and so I want to head back to that and give you a bit of a review. So the overall rate law for a reaction has a few rules. First off, there can be no intermediates or catalysts in this overall rate law. And the rate law that's predicted must match experimental observations. Okay, so let's make sure that we know what an intermediate or a catalyst would look like in a series of elementary reactions. So if we have A going to form B, and then B going to form C, B is what we call an intermediate. It's both a reactant and a product. The other thing, the catalyst, if we have A plus B going to form C, and then C going to form D plus B. B is a reactant and then a product, and this means in this case, it is a catalyst. So it's involved in the reaction, but it's not used up. It's used and then it's recreated, and that's what a catalyst is. An intermediate is something that is created and is then used. So intermediates and catalysts are really kind of opposites of each other, but they have very different roles in the course of the reaction. Okay, so if a mechanism has a slow first step, the slow step is what in general chemistry we called the rate determining step. An example of this is when we have 2NO2 going to form NO3 plus NO, and that step is slow. And then NO3 combines with carbon monoxide to form NO2 plus CO2. So when we have this case, we can determine the rate of the rate law directly from the slow step. So the slow step determines the rate law. And because we are looking at these steps, so we can add this together to get the overall, which is going to be 2NO2 plus CO goes to form, NO2 plus CO goes to form NO plus CO2 is going to be our overall reaction. And so since what we have are the mechanisms, so these are elementary steps. Since we have elementary steps, we can directly figure out the rate law from the slowest step. And so in this case, our rate is going to be equal to K1 times our concentration of NO2 squared, because we have our slow step, and so our rate is our rate constant times our reactant, and we can use the stoichiometry of our reactant as our exponent for our rate law. And what we see is that our rate law does not include an intermediate or a catalyst. Therefore, our rate law is good. Now, if our first step is not our rate determining step, we're going to have to do a little bit more work. So in this example, we have a fast step. Our first step is fast, our second step is slow, and our third step is fast. And in this, we have some intermediates. So to start off with, we start off by writing the rate law for our slow step. Now, I chose to put this in terms of the creation of water because water is not my intermediate, but ultimately it doesn't matter. Because remember that this side we could also just write as rate, or we could use the new symbol. So the rate is going to be equal to K2 times the concentration of H2 times the concentration of N2O2. But our challenge is that this is an intermediate. So therefore, my rate law is not complete. And so what I have to do is I have to use this first reaction, this fast reaction, and the definition, we'll use the definition of equilibrium to help us out. So remember that in equilibrium, the rate of disappearance of NO is going to be equal to the rate of appearance of N2O2. This is our definition of equilibrium. And so we can change these rates into the expressions for the elementary steps, into the rate laws. And so we get K1 times the concentration of NO squared is equal to K minus 1 times the concentration of N2O2. And so all I did here was I rearranged so that I solved for N2O2, which is my intermediate. And so then I can take this and I can plug it into this expression and I get my overall rate law. Okay, so this process of set the rate law based upon the slow step and then find a way to solve for an intermediate using one of the other reactions and plug things in to get rid of that intermediate. That's the sort of process that we are going to be using as we work to figure out what the steady state approximation is and the fast equilibrium approximation. So hold on to this information, and because we're going to use it on the next set of videos.